when we need to evaluate the area under the surface along some curve C, we would use the line integration. If this curve C is given as the vector function r of t, which has the t components, some function of the x of t and some function of the y of t, this integration would become the integration of the f, x of t, y of t, and I would substitute the ds was the magnitude of the r prime, and I would integrate this with respect to the t, where t changes from t1 to the t2. Now, so we would like to evaluate the work which we need to do in order to move the objects along some curve r of t in a vector field f using the line integrals. So in order to define the line integrals in the vector fields, let's talk about the work which we have to do in order to move the objects. So let's say we are given some object and we would like to move this object along this vector d for the distance which is the magnitude of this vector d. So let's say its magnitude is equal to the t meters, and the magnitude of the force is equal to the 5 newtons. And let's assume that the angle between this vector of the force and the vector which we have to move in is 60 degrees. And the work which we have to do is the magnitude of this vector, d, multiplied to the projection of this force vector onto this vector d. So I can find the length of the projection by multiplying the length of the vector f to the cosine of the angle between them, which is cosine of 60 degrees. So if I substitute everything here, I would get the t meters multiplied to the 5 newtons multiplied to the cosine of 60 degrees, which is 1 over t, and I would get 5 meters multiplied to the newtons, which is joules. So in general, I would write down the work which I have to do in order to move this object along this vector d as the magnitude of the vector d multiplied as the magnitude of the force multiplied as the cosine of the angle between these two vectors, and this is nothing else as the dot product of the d multiplied as the f. We've learned about the dot products previously, so the angle between the two vectors can be defined by multiplying the t vectors as a dot product and divide them to the multiplication of their lengths. So in general, we can write down the formula for the work, which is obtained by multiplying the t vectors as a scalar product, as a dot product of the vector d, where we have to move the vector in the force vector. Now let's talk about the line integrals in the vector fields. So let's say we're given some vector field in general in this form, and some curve inside this vector field. What I want to do is I would like to move this object along this curve inside this vector field, and I would like to evaluate how much work we have to do in order to move this object. So in order to do this, let's split this curve to the many small pieces where the lengths are going to be always the same. The arc lengths of the curve between these 2 points would be always delta s. Let's zoom this in this place in order to see this more precisely, what is the idea of the line integration. So this piece is like this, and our point is here, and we need to move this in this direction. So I would calculate the tangent line here, the unit tangent line here, and the force which we have to apply is this f. So this is the situation. So I need to move the object from here to here, and this would be the vector t, the unit tangent vector t multiplied to the d delta s. So if you remember, so if you have some unit vector I with the components 1 and 0, if you would like to get another vector in the same direction, you would just multiply this I to the length of that vector. The same is here. So if you have some unit tangent vector, if you would like to move the object in this direction, so that the length of this vector would be equal to the delta s, then I would just multiply the t vector to the delta s. Because if I take the length of this, so since delta s is a constant, it would be the constant multiplied to the norm of this vector t, and since the t is a unit tangent vector, it would be simply delta s. And we've learned before that the work which we have to do in order to move the object in a small piece would be roughly equal to the f vector dot product to the t multiplied to the delta s. And we can take out the delta s from the brackets, and I can write down this f dot product as a t multiplied as a delta s. So this would be a work which we have to do in order to move this object in this small piece. So in general, if I would like to find the overall work, I would just take the summation of the work for all the pieces. It would be f dot t multiplied as a delta s. And you see, so I'm doing this approximately because my vector is not along the curve. So in order to increase the accuracy of my calculations, I would just take the limit of the summation when n goes to infinity, which is the f dot t multiplied as a delta s. So this would be the definition of the line integral in the vector fields. So this is the vector field multiplied as a unit tangent vector, and we have to integrate this with respect to the arc lengths. So at the same time, if you remember, we defined the arc lengths, so ds, as the r prime and its norm multiplied as a dt, and I would like to substitute this here. And at the same time, if you remember, so the unit tangent line was the r prime of t divided to the norm of the r prime of t. So let's substitute everything here, and we would obtain the line integration would be f dot r prime of t divided to the norm of the r prime of t multiplied to the norm of the r prime of t dt. So we would cancel them out, and what we'll have with the line integration is f dot r prime of t, and we have to integrate this with respect to the t in between the t points, between t1 and t2. Let's consider an example of calculating the line integral in the vector fields. So we would like to move the object from 0, 0 until 1 and 1 in the vector field, which is given as y squared multiplied as I plus x squared multiplied as a j. So we could write down them as a t-tuple, y squared and x squared in this way. So let's draw this. What we would like to do is we would like to move the object from 0, 0 point until 1, 1 point in this vector field. And let's move this object, first of all, along some line between these 2 points. So first of all, we need to derive the equation of the line segment. So the equation of the line segment can be obtained by multiplying the initial points, initial coordinate of the initial point to the 1 minus t, plus the ending point of the line segment, xy and y1 multiplied to the t. So in our case, x0, y0 is 0, 0, multiplied to the 1 minus t, and the ending points is 1 and 1, multiplied to the t. So what we would obtain is t and t. So this is the vector equation of our line. So this is r of t, which is equal to the t and t. And the work which we have to do here in order to move the object inside a vector field would be equal to the line integration of the f dot r prime, and we have to integrate this with respect to the t, where the t would change from 0 to the 1. So let's substitute everything here. So from 0 to the 1. So when we are given the curve with this equation, the first component means the x is equal to the t, and the second component means the y, which is also equal to the t. So when we substitute the f with the components y squared and x squared, I just need to substitute this with the t as well, first of all. So this is going to be t squared and t squared multiplied as a dot product to the derivative of this vector function, which would be 1 and 1. So if you take the derivative of this vector function with respect to the t, it would be 1 and 1, and we have to integrate this with respect to the t. So the dot product of these two vectors would be t squared plus t squared, which is t squared, and we have to integrate this from 0 to the 1 with respect to the t. So the antiderivative of the t squared would be 2t cubed over 3, and if you substitute 0 and 1 to here, we would get simply 2 over 3. So the work which we have to do in order to move the object from here until here along this line would be 2 over 3. So now let's move the object from this point 0, 0 until this point 1 and 1 along a different curve, which is given was the vector function t and t squared. So in our case, in the new case, r is given as the t and t squared The derivative of the r with respect to the t would be simply 1 and tt. And our vector function, which is given as the vector with the components y squared and x squared, would be equal, when I substitute this is going to be the x, and this is going to be the y, and I would substitute them to the vector function. It would be t in the power of 4 and t squared. Now, in order to evaluate the work, we just need to integrate the force, the vector field, multiplied to the r prime as a dot product, and we need to integrate this with respect to the t from 0 to the 1. So this would be the integration from 0 to the 1 of the vector t4 and t squared to the 1 and tt. So if we multiply this t vectors as a dot product, it would be t in the power of 4 plus t in the power of 3, and we need to integrate this from 0 to the 1 with respect to the t. So the antiderivative of this would be t5 over 5, and the antiderivative of the second one would be 2t4 over 4. So if we substitute the 0, both of the terms are going to be 0, and if we substitute the 1, we will get 1 over 5 plus 2 over 4, which we can write down as the 1 over 2. And if we give the common denominator, it would be 5 plus 2 divided to the 10, or simply 7 over 10. So the work which we have to do in order to move the object from this point until this point along the second curve would be 7 over 10. And along this curve would be 2 over 3. And obviously the work which we have to do in order to move the object along the first curve, along the line, is smaller than this work.